This is unnecessary info.
Yes.
I need to turn this is. Do you kidding me? No. You know, you guys are terrible.
I will say one thing, we do a lot of.
You're a tech wizard.
Discussion, and I also asked to vote on raising,
What?
so we need one of these.
Not a wizard?
Make sure to sit next to
That's
someone.
a lie. Thank you.
Good morning.
Tech warlock.
Let's see.
Have you ever played D&D, Kamani?
Is a little-
Have you ever played D&D?
Sorry, but
Do you want to play? I'm not offering, but
this is us to vote on things sometimes, so.
maybe.
You
should, it's fun.
And to us students also to discuss, so you want to make sure to sit next to someone. Don't rate it.
I did the demo.
Yeah.
I rigged it.
Yeah.
See you. Thank you.
Yep, thank you.
No, oh my God.
Miss you.
I miss you. Look, this is my friend, it's my big house, man, like this guy. No, my.
Okay, no way if I put it here.
How much longer are you on the?
Oh,
I don't know, it's until like it starts feeling better, but
Okay.
I've been trying to walk without it. And I can totally walk, but if I walk too long, it starts to hurt, and so.
So it's like physical therapy in between or?
Oh, I haven't started physical therapy, but I should do that.
The first time I turned it in, a week after it was due. I'm changing. No, that's not. No, okay, so this is not my pre-run. This is another visiting student. Yeah, my prefrontal cortex. So there's another one. That's great. Yeah, actually, they're all.
No.
They're all like. You're from California.
That's not LA.
That's the same thing.
I lived an hour and a half.
You've been gentrified.
But like you're actually
You are.
guys, I'm mean that's good. Oh my God, that's so good.
Maybe I'll see you.
It's my.
So we do a discussion. So it's 50 minutes.
There's something. Would you do like that?
Oh my God, there's. I didn't know.
It's.
Pretty nice. Yeah, I was taking a look at it before this. It set everything up. It got easier. It got, and part of it. Yeah. It got harder and then it got easier. I can figure out number one pretty well. Yeah.
We might just overthought for everything.
Really?
Oh my God,
We'll fix it, don't worry.
I have to drop out of the class.
You just want an excuse, don't you?
Great start.
big ass.
Okay.
Yeah, I have. It's funny, man.
But that's what I said. Today. Sure.
Just sit, you're sitting. Sit up, listen to this, Jimmy. I mean, it's like. Yeah, so it's not that big of a deal. You don't do it, right? Oh, yeah.
Point. Okay.
Having a watch shift on Sundays.
I didn't know.
Against like making sure that everything's okay.
I got my phone.
And I realized I have to shift at least more at night. I said no. And so I had to go up with my late night shift.
Okay. Alright, so. Welcome back from the weekend. Only 1 week to go to the full week. I know that last week we had no quiz and no homework because of the midterm, but this week we're back to the usual. So reminder, there is a homework due tonight. And quiz due this week. Yes, all right. So last time we were talking about work and we'll continue with that, but then slowly start to edge into energy and friendly extension. Stay. Can anyone remind me if we did this problem? No. Okay, no, then let's think about this problem.
I did make like.
And so we have apple, which is on the lower shelf. Student picks it up, changes their mind, puts it on top shelf. And we're asked what the total was done by all of this. Anyone need more time? Bit more time. Alright, get ready to vote. Show what it is. Okay, one between A and C. So remember that, okay, so let's just recap a few things. It says that work is integral f dot dr. Initial to final. And this is going from some initial position to some final position with work done on the system. And if f is constant, this simplifies to just f dot delta r. All right. But in this case, we have, I mean, gravity is constant, but we have also like the force exerted by the student. It's not constant, right? So that would be a bit hard to do using this. But we also have the work energy theorem, which specifically talks about total work. It says that the work total on a system is equal to
The change in kinetic.
the change in kinetic energy is equal to delta K. Right, so K final minus K initial. Right, so if I ask again, take a moment to think and then reconsider this problem and then show me what you think. Okay, yes, all right. So everyone, well, most people on C. So yes, total work is zero in this case. The total work is zero, right? Individual forces may be doing positive work or negative work. The total work done is going to be zero because it starts at rest and it ends at rest. And so the kinetic energy initial is zero, the kinetic energy final is okay. In fact, we can say that will gravity be doing positive work or negative work? Negative work. We can say that because the overall displacement is upward, right? But the force of gravity is downward. And so since those point in opposite directions, we'll get negative work from the dot product there. So gravity is doing negative work. And so that tells us, oh, the student must be doing positive work on question. Yeah.
How does potential energy affect profit?
So we haven't yet gotten to potential energy, but I will say that, I mean, notice that if you're talking about the total work, there's no potential energy on this side, right? There's only kinetic energy. When we get to potential energy, I'll show you how that also plays into that. But this is true, that the total work done is just equal to the change in kinetic energy. Other questions? Okay, then let's try this problem. Force acting on an object, told how much it moves, its direction, and we're asked for the work. Won't give you too long.
After auto racing. Yeah, because I'm ready for this problem.
All right, anyone need more time? Bit more time. All right, show me what you think. All right, mostly for B, B is correct, yes. So in this case, the force is constant, so we can use F dot delta R. Since F is constant. And we have 3 newtons, let me just do 3 I hat minus 4 J hat newtons. And the displacement is 5 meters in the negative I hat direction. So we have minus 5 meters I hat. And we're doing a dot product. And so when I do I dot I, what do I get? Well, when I take the components into account as well, yes, I'll get negative 15. But if I just do I dot I, 1, yeah, have the confidence to say it, yeah, 1. If I do J dot I, 0, because they're perpendicular, right? So when I do this dot product, yes, I end up with minus 15. There's technically an I dot I, but that's going to turn into 1. And then we have Newton meters, right? And so we have minus 15 Newton meters, but a Newton meter is just another way of saying a joule. If the work done is minus 15 joules. One of the reasons I'm sort of harping on this I dot I is one is this is part of that transition from two vectors turning into a scalar quantity. All right, questions? No. Let's try this. So take your notebooks out, Even if you can do it in your head, try and write it out. And pay attention to the signs. So we're using the work energy theorem in some way, so starting from that, see how we can simplify the two sides. If I know it's enough, and then on the other side, we would have work done by friction, which in this case is a constant force. So we can we're using the work energy here for leading work achieved. Honestly, don't remember. So the initial kinetic energy is the optimal thing. What are the chain bonds? No, further discussion. Give you a little, talk it out with, your neighbors.
And we know our initial. So I plugged in that and oh yeah. And then we know our is 0 because it's coming from red. So and a final means 0. So I have this.
Oh, except the, it's like.
Then.
That's what that's
I was thinking about that. Technically, it's negative. But other than yeah, so what is that? That is also work. So what is the force for us? Yeah, so
This is just true.
I mean, it's just a distance. Which is why
Okay. Let me see what people think. Okay, mostly for E, which I haven't done the calculation, but I assume that's correct. But let's just dip into the process a little bit. Yeah. I've moved the screen up for a moment. So we have work total equals the K. And in order to break down this work total, I need to figure out what forces are acting on the object. So if I draw a free-body diagram of the object, I have mg, I have the normal force Fn. I'm going to assume that it's moving to the right. And what other force do I have? Friction. What kind of friction? Kinetic friction, because it's sliding, yes. And that is going to be to the left. All right, so I have these. So technically my work total is going to be the sum of three things. It's going to be work done by gravity, plus work done by normal force, plus work done by friction, equals delta K. But these two are zero. Why? Well, yes, true, they do cancel out, but even more fundamentally, individually, they're zero. Yes. To Yes, exactly. Yes, they are perpendicular to the motion. Yes, that's correct. You're always looking at the angle between the force and the displacement, or the force and the velocity. And so these are at right angles to the velocity, so they don't contribute. So the work done is zero, work done is zero. So we just have work done by friction equals delta K, which is K final minus K initial. But we know that the final kinetic energy is zero. So this just becomes zero minus 1/2 mv initial squared. And on this side, the force of friction is constant. So I can simplify it to F friction dot delta R. On this side, we just have minus 1/2 mv initial squared. Here, I can do the dot product in multiple ways, but most simply I could do magnitude of the force of friction times magnitude of the displacement, I'll call it d, times cosine theta. And this is something that people forget often. You do need to account for the angle between the force and the displacement. In this case, what is the angle between the force and the displacement? 180 degrees, not zero, right? Because the displacement is to the right and the force of friction is to the left. And cosine of 180 is? -1, yes, that's right. So we get minus F friction times D equals minus 1/2 mv initial squared. And so the minuses cancel, and we know the force of friction, so we can solve D equals mv initial squared over 2 times the force. I want to be clear. I mean, a lot of you maybe weren't thinking very carefully about the signs, but you got it and you knew when you could get oh, I don't need the minus sign here and got rid of it and whatnot. But it pays to be careful in your thinking and keeping track of the signs, because often that will help you, it'll help you avoid going down wrong paths. So, yeah, it pays to keep track of signs and see where they come from. Questions?
I can only see it like.
Oh,
Okay.
yes? Okay. Yes. Oh, this one? Yeah. Yeah, no, but obviously the reason I can't keep it like that is now I can't see the screen. But yeah, temporarily. All right, other questions? All right. Yes, Elias?
Oh, no.
No, okay, all right. Oh, yeah.
I just wanted to comment on when like on the first part, when we say when done of gravity and almost zero,
Yes.
do we consider the 90 like the angle relative to the velocity or relative to the acceleration? Like
To the velocity, very good question. Yes, relative to the velocity. Yeah. Yes.
If let's say if everything here was the same except it was in reference to its vertical motion, would then the change in R be d sine of theta instead of d?
Oh, no, so the cosine here is not because it's in the x direction, it's because it's a dot product. Okay, right? So this is part of the definition of the formula for the dot product. And this cosine is specifically, it's the angle between the force and the displacement. Other questions? These are good, important details, so I'm glad you clarified. Okay. Let's again, I'll put the screen down again. It's a fairly quick one. I won't give you much time on this. Your pendulum is in the process of swinging from its highest point to its lowest point. During this time, work done on the pendulum by gravity is. All right, and show me what you think. Okay, yes, people, for A is correct. It is gravity is doing positive work. Now I'm just going to ask almost the same question. I've changed one word. Okay, so. Right, show me what you think. Okay, all three camps are represented. Go ahead and discuss.
How did I get perfect? Yes. My first guess. This is negative.
Not straight up. To the string, yeah. Tangential is, yes. So.
I
just needed like.
Oh, wait, I think it might be zero. Velocity.
So if it was
And if you think about like speed, speed is always constant. There's no change in kinetic energy. I think the force of tension.
So in the water, you did like aspiration.
Yeah, but do you agree, or do you have like find other causes?
Do I agree on like that?
Do you agree on what I'm saying, or do you like?
No, I agree. I think let's look at
I
it.
think I heard the discussion right down the road, so it looks like people have reached
I think
consensus.
it's
Get ready and show me what you think. Okay, most people for B, B is correct. Here. Would you find the shot? William, sorry.
Oh, William.
Yes.
Sure, so we're looking for tension, and tension is always going to end up being perpendicular to your velocity no matter where you're going, so the work done will be zero.
Yes, that's exactly right. So the tension is along the string, whereas the velocity is tangential to the circle, and so it's at 90 degrees to the tension. And so that stays throughout this process, and cosine of 90 is 0. So yeah, it does 0 work. Now, if you one way that some students find sometimes helpful, but you have to be careful with it. You can think of it as, oh, the tension is slowing it down in the vertical direction, right? So it's doing negative work in the vertical direction, but speeding it up in the horizontal direction. So it's doing positive work in the horizontal direction. And so the total work done is 0. So this is correct, but I do caution you about thinking this way because remember at the end that work is a scalar quantity. It doesn't have components, right? So in the end, we have to add up all those contributions and just get a single number, which is 0 in this case. So yeah, so the tension doesn't speed it up or slow it down overall. It just changes the direction in which it's moving. It redirects it. Questions? Okay, so yes, demo question. You have the demo set up over here. Simple pendulum, ball on the end of the string. I'm going to raise it to the level of this 2-meter stick and let go. And the question is, when I do so, when it swings to the other side, will it swing to lower height, equal height, or higher height? Won't give it too long. All right, show me what you think. Okay, some people suspicious, but most people say equal height, and that is correct. It should be an equal height, at least for the first swing. So let's check that out. Yeah, reaches an equal height for the first swing. After that, it starts to die down, partly because of air resistance, partly because there's some flexing going on here and it's losing energy there. But for the first swing, we saw that it went up to the same level. All right, that wasn't very tricky. However, my next question is, what will happen if I released it the same way, but then I introduced this bar into the path so that as it swings, the rope is going to like wrap, not completely around, but like it'll be influenced by this path. Now, will it go to the same height or lower height? You know what? Go ahead and discuss.
I guess your life all the way. I don't know. I know from prior knowledge that pendulum like pendulum swing always depends on not with the feet. Pendulum. I think. I don't know, well, it's gonna hit that height and it's gonna go. I'm guessing it's probably. Think about it, I'm guessing it might go to like a bit higher, like it has it hit now it has a short. Kind of like, oh wait.
Okay. I know this one is this one's a little weird because you know there are little bits of like personal experience and like it should do this and do that. All right, let's see what people think. Okay. Interestingly, mostly between B and C, no one's going for A. Let's take a look at what happens. All right, and so we're just looking at the first swing. Right, so from the same height and it's roughly straight. Yeah, okay. Oh, yeah, went to the same height. Okay, so yeah, the answer is equal height. The answer is B. Okay, so let's look at this in a bit more detail. one thing I want to point out is that we didn't swing enough for it to like start wrapping and actually decrease like the roll. I know that some of you are thinking about like the wrapping around the pole sort of thing and like, oh, it speeds up as the radius decreases sort of thing. But that's not the sort of thing to focus on here. Okay, so yeah, let's put up the board and talk about this a little bit. So similar sort of starting point, we're starting with the total work equals change in kinetic energy. And so if I break this down into the work done by various forces, what are the contributions? I have the work done by gravity and work done by tension. But we also just showed that the work done by tension is zero. Yes. This one can be negative. And so those are the only two. Yeah, so here we have K final minus K initial. And which points do you want to take as your initial point and your final point? There are a couple of choices that make sense. You guys tell me what you want. Yeah.
When it's about to be dropped is like the initial.
Okay, so initial when released, and then final, I guess, when it comes to a stop on the other side, right? Okay, so when released. And then when it stops momentarily. All right. All right, so this side actually simplifies very quickly because when released, its velocity is zero. And when it comes to a stop, its velocity is zero. So this is just going to be zero on this side. So we get the work done by gravity is zero. Luckily for us, gravity is a constant force. So even though we start out with this full integral, this is going to simplify. But let's look at the process in a bit more detail. What's the formula for the force of gravity? mg, that's the magnitude. And if I want the direction for a vector, negative mg j hat, yes. So I'm going to set up my coordinate system with y as the positive direction. And so this becomes minus mg j hat. Integral. What about my dr? What can I expand that out as? Talked about this once, only once I know, so don't blame me if you don't remember, but ideas? Alex?
dx or di hat plus d.
Yeah, you're basically there. This is, remember, it represents a small displacement, right? It's a vector quantity, so in general it will have I, j, k components. So there will be an I hat component, but that's talking about just the displacement in the x direction. So it would be dx I hat. And then we have, oh, there's a y component as well. And there's a z component in general. This would be your dr. All right. But then I do the dot product. And what is j dot I? 0, you said that. And j dot j? 1. And j dot k? 0. Yep. And so when we do this dot product, this simplifies to minus mg dy. I'll give you a moment to catch up on writing. This is from initial to some final. Any questions so far? Yes.
It's not necessarily a question about that. Guessing from how you're writing it out, it probably is easier to think about it like that, but we also thinking about it as like the angle in terms of an angle and a radius.
I think that would make it a bit more complicated, but it is true that will in the end give you the same answer, yeah.
Okay.
Other question? No? Okay, and what is the variable of integration? Y, right? So the d is attached to the y. So that tells me that the bounds of my integral should actually be y initial and y final. Okay, so we have this, and on this side we just have 0. It's equal to 0 because there's no change in kinetic energy. M and G and the minus sign are constants, so I'll throw them out. Show y final 0, and integral of dy is just y, so we just get minus mgy evaluated as y final and y initial equals 0, and so we get minus mg times y final minus y initial equals 0. And the only way that's going to happen is if y final equals y initial. So yeah, it goes up to the same height. Questions?
I'm sorry, could you just go over why we had switched to J hat? Just,
Well, no, it's simply that I wanted to do this integral, right? And so which way is gravity pointing?
in the negative one.
Yeah.
Okay, good.
Other questions?
I guess this is how you think about it mathematically, but is there a way we could think about it conceptually as well?
Yeah, you could say that the only force doing work on it is gravity, right? And so whatever kinetic energy it builds up in going from this height to this height, it has to lose, right? But because gravity only acts in the y direction, we're only caring about displacement in the y direction. So whatever, it picks up energy here, it needs the same amount of distance to lose that energy.
Okay. Makes sense.
Other questions? Okay, all right. So just again, sort of recap important points. We started the work energy theorem. We split it up into its different contributions. We discover some of them are 0 and evaluate the kinetic energy side. And then with the work side, work of gravity side, we did the integral. I could have sort of jumped straight here if I just used the fact that gravity is a constant force, right? And then I could just do F grav dot delta R, and then the dot product would again pick out just the y component because the mg is in the negative j hat direction. Okay. All right. So yes. Well, okay. No. Let me just introduce. Since we talked about gravity, let me just introduce a concept here. So one thing we notice about this calculation here with gravity is that in the end, the work done by gravity only depended on where it started and where it ended, right? And another example of that is I could like put this chalk on the floor, pick it up, put it on the table, and when I do that, gravity does some work, right? Or I could start with the chalk on the floor, and then put it on the table, and gravity does the same amount of work in both cases, right? So what we see is that gravity is a special force because the path taken does not matter, right? Only where it starts and where it ends. And so this is one of the special category of forces, which are called conservative forces. And they're characterized by the fact that the work done is path independent. Now, as a consequence of this, supposing I take an object and I move it in some path and I bring it back to its starting point, what can we say about the work done? It's 0, right? So that's another way of characterizing these conservative forces, is that you can take an object through an arbitrary path, but as long as it ends back where it starts, the work done will be 0. Now, gravity and the spring force are going to be sort of two of the most common ones we see in this course. But as we move further into 116, like electrostatic force is a conservative force, and so on. Friction is not conservative. One way we can see that, we can imagine, oh, if I take this box, I started here, and I slide it along some path and bring it back to its starting point. The work done by friction, what can we say about it? It's different from zero. Is it positive, negative, is it positive or negative? It does? No? Okay. Anyone? Oh, yeah, done.
Negative,
Why?
because it's always opposing motion, and it's also, if you could think about friction as slowing it down, so it's always changing the kinetic energy. It's always decreasing its kinetic energy.
Yes, that's right. So in this case, the friction is in the opposite direction of the velocity, right? And so it's always doing negative work, even when it comes back around. In the case of gravity, right, when I'm thinking about gravity, when I raise it, gravity is doing negative work, but when I lower it, gravity is doing positive work. And so once I come back to the starting point, those two contributions cancel out. But with friction, when I move it this way, velocity is this way, friction is this way, it's doing negative work. When I move it this way, oh, the friction reverses direction. Now the friction is this way, the velocity is this way, still doing negative work. And so overall, it's doing negative work, and it's not a zero when it comes back to the start. Yes?
Does friction always do negative work?
No, friction can do positive work as well. Yeah, but the point is that it is like this definition with the conservative forces is for like an arbitrary path. It should be zero when you do a closed loop, whereas that's not true for friction.
Is it fair to say that conservative forces always act in the same direction relative to an object? I mean, like, I know, for example, like gravity, it always acts towards the center of the earth. Is it like fair to say that conservative forces always act towards, or are always constant in direction towards some, in respect to something?
I wouldn't want to make that a definition, but it is characteristic of most of the ones we see, yes. It's definitely true that they depend only on the coordinates, but that alone is not enough to define a conservative force.
Okay.
But yes, it is a characteristic of most of the conservative forces.
When would friction be doing positive work?
If friction is helping bring something into motion. So like the box on top of another box sort of thing, and you start moving the lower box, friction is doing positive work on the top box. Then again, friction is doing negative work on the bottom box, but yeah, if you're just looking at one part of the system, yeah. Okay, let's try one more voting question. Two more actually. We just have time. Okay, so we have an object, mass is given, subjected to a force points in the positive x direction, object starts with initial speed of meters per second. And for simplicity, we're going to assume the object moves only in the x direction and it's initially moving in the positive x direction. We're given the initial velocity, and the graph shows how the force changes with position. And so the question is, when the object reaches x equals 6 meters, what is its kinetic energy? Give it another 30 seconds. Anyone need more time? Bit more time, okay. All right, let's see what people think, at least initially. All right, we've got a variety of answers. Go ahead and discuss. I will give you one bit of information. The answer is not C. Is calculated, yes, so that I solve.
Okay, so work is equal to.
Yes.
Yeah.
So,
Oh,
yes, delta K in the.
I know
is
it's
four.
four.
So K final minus four is 3 joules. So K final. That's a K initial, that's an important part. So let's write out the equation, so what we have is work.
So I know, we know that it's gonna be F.
Work equals what quantities do we know what the force
Do you say it's F delta R, which is?
do we know?
Initial and.
Oh, wait.
So we're trying to find the K final.
So.
That's what,
Oh, I know.
that's the way I thought.
So I did my calculation. So if you take the area of the graph, the work done, so W, which is equal to KE, and then divide KEI by doing 1/2. Sorry.
Apply that.
Okay.
So define the initial kinetic energy by multiplying by squaring the initial velocity with the work. KE, and then you find KI.
Now, we're gonna take
Four squared. Which is 16 divided by 2, which is 18 divided by 2 is 4. And if you add 4 to 3, 7 and 7 equals KF. And do you understand how to get the work? And how do you get that from the graph?
Oh, so it would be.
I think 2 weeks ago.
So if we have 1/2
Every week.
Yeah,
I have 4 tests.
Okay.
Wait,
Let me see, quick vote. Alright, E is correct, yes. Thanks. And so, what do we see? We see that, the area under the curve is the work, but always remember that, these area under the curves will correspond to the change in some quantity. And so here the work corresponds to the change in kinetic energy. So we have work equals K final minus K initial, but your K initial is not 0 in this case. And so if we calculate what K initial is, we get that K initial from 1/2 mv squared is 4 joules. The area under the curve is the work total, that is indeed 3 joules. So if we move that over to get K final, we get K final is 7 joules, 4 joules plus the contribution of 3 joules. See some slight hesitance in a couple of faces. Yeah, Elijah.
Can you just repeat that, like?
Sure, I know, I was rushing a little bit. Okay, let me just write it out over here. we have work total equals delta K, which is K final minus K initial. On this side, the work total is just going to be the area under the curve, which is 3 joules. We're trying to find K final, and K initial is 1/2 m V initial squared. We know the mass, we know V initial, right? And so if we calculate what the K initial is, we get 4 joules. So we get 3 joules is K final minus 4 joules, so K final is 7. Okay, we are out of time. Okay, all right, yep, we are, so I'll stop there. We'll do one more work question next time and then move on to potential energy.
And I bet he's still at this waiting. What? It's yours. I like 8%. It's a hard, it's a hard one. You small.
I was like, Claire, we're.
Yeah, oh, that, there we go.
I think he's gonna add something to this series. I don't.
Yes.
I was like.
Can I ask you like a question back about friction? If you have two boxes that are say there's no friction, but is friction in the two boxes? If you put a force on the bottom, is the static friction in the opposite direction?
Static friction on which one?
Is the static friction from A on B?
Which one is A, which one is B?
Oh, sorry, top is A, bottom is B.
Okay.
So is the static friction on the bottom from the top
Right now,
going to
really bothering me.
propose the motion of the bottom, and if there's no friction underneath the bottom?
Yes.
It's
opposing the relative
You
motion.
feeling
between-
something like stress?
right, but because the top box is gonna move with the bottom box.
But it only does that because of the friction of the bottom one exerts the problem.
So there's
I feel like
so
I'm moving
the
down.
force of, there's two
Oh,
forces
yesterday a bunch of
preventing the
snot.
movement of the bottom box,
Ah.
the static friction with the ground and the static friction of the top.
We use the bottom, the ground.
Right.
So yeah, so then just the top one.
Okay, okay,
So,
thank you.
yeah, there was a bunch of snot in my eye and it was rubbing it out, so now my eye was all swollen.
Okay, all right, okay.
It was not.
We went back.
Thanks, Rick, I really appreciate it. I've got to rush over to this.
Oh, you're real for that. You
Yeah.
you 1150 is that your
Yeah.
That's crazy. I couldn't imagine.
Um,